Good evening, everyone. Okay, let's get started. Actually, let me just turn down the music a little for me. I hope that's still okay for everyone else. So, last time that we were here, we reworked all of the inputs support for Kaji. So we added fpuzzle loading, and then we checked ourselves by loading in a Piggly Wiggly puzzle, which, if I remember correctly, let me see if I can find it. Oh my goodness me, where's Piggly Wiggly? There's Piggly Wiggly was an irregular 6x6. So what I'm going to do is suggest that we stick with 6x6s, but that we move on from the stuff that we currently support, and we're going to add a new constraint. Now, at the moment, our solver does not have the concept of the value of cells. All the symbols are just that, they're symbols. So we're going to do a constraint that doesn't require us to think about the value, because that constraint is defined in terms of the symbols. And the constraint that we're going to go with is called quads, or quadruples. And I have prepared a puzzle in fpuzzles called Quad Bike, which is one of my tutorial 6x6s. And my hope is that this will turn out to be a reasonable puzzle for us to use to design a quadruple solver. So the first thing I'm going to do with you all is I'm just going to take us through solving it, because we may as well have that recorded. So if I switch the mode into solving mode, then the rules about quadruples, which are these circles here, 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 and here, is that in the cells that are touching the circle, the digits that are present inside the circle must be present in those cells at least the number of times that they're present in the circle. So this 4, 5 here tells us that there must be a 4 and there must be a 5 in this quadruple, but it doesn't tell us where they go. So if we ignore the givens for a moment, the 4s might be there, and there might be a 4 there, there might be a 4 there, you know, it doesn't really matter. The givens are what will end up constraining this. So if we look at this grid, then one of the first things that we can do is we can see that there's a 3, 4 there and a 3, 4 there. So that means that the 3s and the 4s in these two columns are taken up. So the 3s and 4s in these columns can't be in that box and can't be in that box. We can see the 4, so there's our first digit is a 3. We can then do an interesting thing here with the 4s and 5s. We said that there's got to be a 4 and there's got to be a 5, but these two cells see 4 and 5, so they can't be part of this. So these two cells must be 4 and 5, and this one sees that 4, so there's our 5 and there's our 4. Let's continue. So at this point, for reference, this quadruple is now exhausted. There's nothing more that it can tell us because we have a 4 and we have a 5. So if we move on, we know that there's a 5 here. We know it can't be here. We know it must be here. This 5 sees that, so that has to be a 5. And in reality, at this point, we've got that 5 looking up, we've got that 5 looking up, and we've got that 5 looking across. The quadruple wouldn't have helped us anyway, but we've got that information, so we may as well use it. This 2 looks all the way across and eliminates 2 from those two cells. So in this quadruple, the 2 that it needs must be there. And now, just for completeness, we know that there's a 1 and a 6 there, and at the moment we don't know which way round they go. So let's come across and look at the left-hand side of the grid. This column is almost entirely full. If we look at those two cells, they need to be a 1 and a 6. This 6 looks across. So there's our 1, there's our 6. We think about these two cells. They see a 3, So they can't be the 3, but they could yet still be a 4. And they could also be a 1. So that's a 1 and a 4. So we know that the 4 is in the bottom row. In fact, we know that the 3 is in the top row here. We know that it's a 3 and a 2 up there. But the 2 here C's. So we can say that that's the 2 and that's the 3. Think we've now got almost all the 2's in the grid. We look the 2 across here, and that 2 comes down. That 5 obviously is given, so there's a 2. And that 2 looks across, that 2 looks down, so there's a 2. The 1 looks across, so there's our 1, and the digit that's remaining in this box is a 3. In this column now, we have a 1, so that must be the 6 and that must be the 1. And we've got 1, 2, 3, we're missing a 4. So there we go. In this column, we've got 1, 2, 3, 4, 5, we're missing our 6. And in this column, we're missing our 1 and our 3. The 3 looks across, there's the 3 and the 1. In our row now, 1, 2, 3, 4, 5. And these 2 are going to be the 1 and the 6 that we're missing, which we still don't know how to place. So let's think about coming across here. We've got a 3 and a 4 here. 1, 2, 3, 6. So 4, 5. And here, 1, 2, 4, 5. So 3, 6. Let's have a think. That 3 looks down and gives us the 6 and the 3, which gives us the 1 and the 6, which gives us the 1 and the 4, which gives us the 5 and the 4. And that solves the puzzle. So that's what we're hoping as an approach that we will be able to get from implementing our quadruple constraint. So let's come back to the setting mode and let's save that solution. And let's clear it and grab the JSON out. So grab the code and copy. Come to here. Sample puzzles. This is called quad bike. And that's entered that in. So just for amusement's sake, if we tell it to load quad bike, and I'm now going to, I'll tell you what, we'll keep this around just in case, but I'll pop it onto the other desktop so it doesn't keep getting in the way. So if we tell it to solve quad bike, it shouldn't be able to. It got one thing. It got a hidden single 5 in row 3, column 2. So that was that 5 there. And if I very quickly bring back this puzzle, that's the 5. And it got that because that 5 looked across and that 5 looked down. So I put the 5 there. So that's actually the first, simple thing to find. We need to teach about quads. So the first thing that we need to do is we need to find the quads in the JSON. So let's bring up the quad bike JSON and let's have a look. There is a quadruple object. That appears to be, sorry, not an object, a list. And each quadruple appears to be an object, which contains cells, which appear to be a list of cells, and values, which appear to be a list of the symbols. And this is one of the really awkward things, of course. fpuzzles is calling these values, but we need to think of them as symbols that are present in those cells. So this is quite interesting, and it should be relatively easy for us to define. So let's go ahead and do that. So in our fpuzzles.rs, one of the rules that we want now is quadruples. No, just quadruple. And it's going to be a vector of fpuzzles quadruple. Nice and simple. if a vector is there, we should probably have set a default to allow it to be an empty vector if there are no quadruples. And let's come along and add our fpuzzles quadruple. So that's going to be debug and deserialize fpuzzles quadruple, and we weren't doing a capital P, so there we go. Remind ourselves what's in that JSON. We've got cells and values. Cells is going to be a vector of an fpuzzles cell ref, I'll call it, and values is going to be a vector of non-zero usize. So there's our definition. We just need to write an fpuzzles cell ref, derive, debug, fpuzzles cell ref, and that's going to have a row and a column. Question: how are we going to get from like R1C1 to a row column? We're going to implement deserialize for fpuzzles cell ref. Think fpuzzles cell ref. And here's our deserialize. And the way that these things always work is that you have to have a visitor thing that then does the deserialization, because we go deserializer dot deserialize str. We give it our visitor, which will be an fpuzzles cell ref visitor, and it's going to give us back the thing that we need. So let's just struct fpuzzles cell ref visitor impl visitor for fpuzzles cell ref visitor. Missing members. So the value that comes out of this is an fpuzzles cell ref. Expecting is, well, we're always expecting a string, but we're expecting a string of the right format. So we're going to go formatter dot write str a string of the form RNCN. And we're going to do visit borrowed str, and this is where we get to actually do our parse. So v is of the form RNCN, where n may be one or more digits. So basically we need to split this up, and one of the ways of doing that is to do some groupings and to do some collecting. Oof. So how are we going to do this? We are going to, can we, so if we go v.chars dot group, no, there's no split, there's no group. Let's take while. But I'll tell you what we're going to do instead. What we're going to do is we're going to take the first character and check that it's an R. So we're going to go first is v.chars.first, which is just .next, dot unwrap what dot expect empty cell ref. I mean, in theory, we should return that as an error. So let's do that. Actually, let's do dot OK or Serday DE error custom empty cell refs not permitted question mark. I think that works. Use of all sorts of things is missing from here. Let's keep going. Oopsie. Need to stick that in. There we go. Undeclared lifetime. Okay, deserialized to behave. We're back to there. If first is not R, and we may as well support lowercase as well. So we'll actually do first dot to ASCII lowercase is not R. Return. And at this point, we may as well. No, we'll stick with doing this. The reason I'm doing this is just because we're going to end up using these things a lot, I'm pretty sure. Cell ref must be of the form RNCN. So we know that the first character is an R. So what we're now going to do is we're going to take the string from the second character onward, split it on the C, and then that should give us the two strings that are our two numbers. So we're going to go let v equal v.to ASCII lowercase. And we're going to say if let sum row column equals v square brackets 1 dot 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 split once on the C, else cell ref must be of the form RNCN. We're going to say row is row.parse .map error e error custom. And we're going to repeat that for the column. So I've got a row and a column, and so it's going to be okay, self value, which is an F puzzles cell ref. So let's just do that. F puzzles cell ref row column manual case insensitive ASCII comparison. Aha. Hooray. EQ ignore ASCII case. Takes borrow. Nice. Thank you, Clippy. And those should be public. And those should be public because it's just data. So we've now parsed RF puzzles data properly. we need to be able to convert that into some information in the grid rules for Sudoku grid data. So let's grab out the Sudoku grid rules data and let's work out what we're going to say here for quadruples. So we're going to go quadruple is a vector of Sudoku grid rules. Quadruple data. Gotta love these great big long type names. Debug but not default. And again, this is just data. So for quadruples, we are going to have some cells, which will be a vector of usize. And we will have some values, which will be a vector of usize. And just to make it clear for ourselves, this is row and column, and these are symbol index 0 based. Row and column 0 based or 1 based? 1 based. May as well therefore make it symbol index 1 based, and we'll do the conversions all in one place. So that's our quadruple data. So let's actually write the parser for all of that. If actually no, we don't even need to do an if. We just go rules.grid grid dot rules mute dot quadruple is our grid data, which is in val. So it's val dot quadruple dot into iter map given an f puzzles quad something and collect. And what we want to do is convert that f puzzles quadruple into a Sudoku grid rule quadruple data. So we're going to go cells equals fp quad dot cells dot into iter dot map. Given the cell, we just want cell dot row, cell dot column. Collect. Now, what did we call it there? We called it values. We really should call it symbols. Symbols is fp quad values into iter map. Given a value, value.get, collect, and then we want a Sudoku grid rule quadruple data cells symbols, and that's converting it all into the rule set. So again, if we cargo run, one sec, that's fine. Grids are there. Here are our rules. Here are our quadruples. So we have a quadruple that consists of cells 1 1, 1 2, 2 1, and 2 2, and needs a 3 4. We have 5 1 5 2 6 1 6 2 that needs a 3 4. 4 5 4 6 5 5 5 6 that needs a 4 5. And 2 5 2 6 3 5 3 6 that needs a 2 5. So those are all of our quadruples. So I'm happy about that. We've successfully loaded the quadruples in. In fact, I'm happy enough that let's do a git add, and let's Kaji loader add quadruples to f puzzles. Kaji rules add quadruples to raw puzzle data. Ah, bad pin. This time. Add quadruples to fpuzzles loader. Now, there's no point in us trying to add quadruples to the Sudoku Maker loader because it just doesn't have them. In the Sudoku Maker JSON, all you get is you get these cosmetic circles and texts. You don't actually get told that they're quadruples. So there's no point in us trying to do anything with that. So Kaji loader now supports quadruples in fpuzzles. And Kaji bin switch to a quadruples puzzle. Now, as we know, that can't solve because while we've added the capability to load it, we haven't written any of the constraint stuff. So let's now start thinking about constraints. Close down the loader, close down bin. And we're going to have to think about the constraint trait, and we're going to have to think about implementing a quadruple constraint. So let's start with the latter because, well, we may as well make the actual process go in line. So in Kaji rules, in constraints, we're going to add a new constraint, and it's going to be called quadruple. And we're going to create that, and we're going to pub use quadruple, which obviously doesn't exist yet. That's fine. And in here, quadruple constraint circle with digits in. So step one, we're just going to convert the information that we have about the quadruple into stuff that we can use with our puzzle solver. So we're going to go pub struct quadruple. We know that we have to derive debug for constraint to work. And remember that we had some cells. So we're going to have cells, and this time it's going to be a vec of cell index because we have to be able to reference the cells in the puzzle. And we're going to have some values, or I'm going to say needed, which is a vector of symbol ID. And the reason that we want that is because those are the symbols that we are hunting for. And we're going to ignore symbol sets that aren't those symbols. And we're going to make the rash assumption that we constructed with symbols with all the same symbol set. Or maybe our loader will decisions. We will validate it in our initializer. So import quadruple pub fn new. So we're going to take some cells, which will be an import into iterator item equals cell index. And we're going to take the needed symbols, which will be an import into iterator item equals symbol ID. And we will return a self. And for now, we're going to go cells equals cells dot into iter dot collect. And we're going to say needed cells dot into iter. Oopsie. I'm really clever. Let's try actually using needed. And then let's return self cells and needed. And we're going to do a quick check here, which is that all the symbols have to be from the same symbol set. So what can we go with for that? We can go needed dot iter dot copied dot tuple windows yeah, the problem is, of course, at this point that we don't know what we're dealing with here, so that's a symbol ID. So dot tuple windows, which is going to take an A and a B, and we're going to go a dot. Oopsie. Let's just do nothing for now. Oh no, it's tuple windows. Map A and B to nothing dot all stood convert identity. And we're going to assert that. And so now we're going to do a dot symbol set is equal to b dot symbol set. And we're going to be told no method named symbol set for symbol ID. And so we're going to go and write that. So Kaji source symbols. Import symbol ID. We have symbol index. We have pub crate set index. We don't want set index, but we do want symbol set ID. Is that part of this? No, symbol set ID comes from puzzle. But we got to use symbol set ID, but that information, I don't think, is actually present. Symbol set ID is used here. Just finish gives a symbol set ID, which does push symbol set. That's why that works. So we want pub fn symbol set. It's actually going to have to be defined in puzzle. So in puzzle, where we have symbol set ID, we have an impl symbol set ID. We have an imp. We don't. These are all little bits. So we're going to have an impl symbol ID. Pub fn symbol set, which takes a borrow self and returns a symbol set ID, and it's going to be symbol set ID brackets self dot set index, because we have to do it around there. So back to quadruple. What's it complaining about now? Use dot all like that instead of dot all and then that. That's fair enough. So we've verified that linearly across it, all of the symbols are in the same set. So that should be good enough for us. We can't actually do any more about this until we start to implement the constraint for quadruple. And we have prep board at the moment that we don't know what we're doing with it, and that's fair enough. We're going to do that. And that's enough for us to get to the point of initializing the constraint, which means that we can now add to the Sudoku grid the ability, here we've got creating the new rules, so the anti-offset rules. Those are rules. And here we have adding constraint given digits. So after we've done given digits, what we're going to have is we're going to have if raw dot rules dot quadruple dot is empty. If it's not empty, we're going to add quadruples. So we're going to go for quad in raw dot rules dot quadruple, and we're going to have to borrow that. So at this point we have the Sudoku grid rule quadruple data, and we need to convert that into what we can hand to the constraint. So if you remember, we're going to be doing builder.add constraint, and the constraint is quadruple new, and it takes some cells and it takes some needed symbols. let's see what we can do to do that. So let's cells needed. Well, the cells should be fairly easy. It's going to be quad dot cells dot map iter map given row and column. And in fact, if I stick a borrow there, that should sort that out. So we've got a row and a column, and we're going to go rows, square bracket, row -1, square bracket, col -1. That should be an impl iterator cell index. So we're good. And now we need to do needed. So that's going to be quad dot symbols iter map given an index. We want to say digits. Don't know. Can I actually find the digit that we want? We can do that by saying builder dot symbols of self dot digits dot so what have we got here? We've got an impl iterator of items of impl iterator. We can do dot nth I -1 dot expect bad symbol index. And that should construct our quadruple rules. And just to prove that, here we will panic. Whoa. Self. Now we should expect to panic, and we panicked with a quadruple whose cells are 0, 1, 6, and 7. So that's that top left quadruple. And the symbols it needs are 2 and 3, which are the values 3 and 4. If you think about it, because it's symbol 2, where symbol 0 is the value 1. So the quadruple has been converted properly. So our next question is there anything that we can do in the quadruples to prepare the board? And if we had a quadruple that had the same number of needed digits as it had cells, then we could constrain those cells. If we don't have the same number of needed cells as same number of needed digits as we have open cells that aren't solved, we can't do anything. So we want to kind of discover, first of all, what the state of the world is so that we can make a call on whether or not we can do something with it. So let's go let qstate equals self.qstate for state. All right. And we're going to have an fn qstate, which takes a borrow self. And it takes a state, which is a borrow solve state. And I've deliberately made that immutable because we don't want qstate to make any changes to the board. We just want it to discover information. And it's going to return what I'm just going to call a qstate. Or I'll call it a quad state because that's the kind of thing that we want to do. I'm going to stick to do, and I'm going to define this quad state struct. And I'm going to derive debug on it because we're going to want to find out what we've discovered. So quad state. What this is going to be is it's going to be what is the state of the board as it stands now? What have we learned? Yeah. So what we're going to have is we're going to have choices, which will be a vector of symbol choice. Indexing is going to map onto cells. We're going to have left, which is a vector of symbol IDs, which will be which of the symbols are left that could be in this symbol choice. Because, you know, let's say, for example, we get to a point where the quad, let's say for arguments is 1, 2, 3, 4 quad, and we know where the 1 and the 2 are, then the other two cells can be constrained to 3, 4 because we need a 3 and a 4, and we only have that number of symbols left. So we're going to have left, and we're going to have unfilled, which is going to be a vec of cell index, and that's going to be all the cells that are left that haven't been filled with a symbol. In fact, let's start with just that and see where we can get from there. So we've got unfilled and left. So the first thing that we need to do is we need to get all of the states. So we're going to go let choices equal self.cells iter map given the cell. Given the cell, we want to retrieve the choice for that cell for the index of the symbols that we're dealing with. And in fact, let's actually pop the symbol set in. So we're going to have set, which is a symbol set ID. And having asserted that everything is good, we're going to go set is just going to be needed 0 dot symbol set. Okay, let's carry on here. So we've got the cell's index. We need its choice. So that's going to be state dot choices given the cell and self dot set. And let's collect that as a vector. So in choices now, we know for each symbol whether what the choices are associated with that symbol. And just because we've computed it, let's include it. It's a vector of symbol choice. So the next thing that we need to do is we need to work out which of these cells are unfilled, as in this unfilled. And that's going to be unfilled is choices iter enumerate map given no, filter map given the I and the choice if we'll map it to none for a moment, and we will collect vec that. So we know that choice is a symbol choice. So if choice dot solved then none, else sum self dot cells I. So that's all the unfilled cells. Interestingly, we can also say that those are the symbols that are left. Found is going to be a vec of symbol ID, which will be the symbols that we have found. Do we need that? No, we don't actually care about the ones we found. We care about what's left. We only care about what's found from the perspective of the digits that we have left to find, as it were. So how are we going to solve that? We're going to go let left self dot needed clone. And we're going to make that mutable because what we want to do is we want to go for each filled cell, try to remove that symbol from what's left. Ooh, okay, for cell in self.cells, it's copied. Choice is state choices cell self set. If let sum symbol equals choice dot single value. So that's our solved value. Left dot remove symbol. Now, let me just double check that removes the first index. Removes and returns the element at position index. That's not what we want. We want to remove an item, not an index. Pop takes the last one. Retain is kind of the opposite of what we want, but we could just... No, because we want to stop on first find. Let's see if there's a better way to do this. So let's pull up the standard library documentation. Let's grab the vector. And let's say remove. And see what it tells us. So swap remove removes an element from the vector and returns it. The removed element is replaced by the last element of the vector. It does not preserve ordering, but is O1. You need to preserve ordering, use remove instead. I think we're just going to have to use find and go from there. So we're going to go if let sum pos equals left dot find. No, find position. Finds the position and value of the first element satisfying a predicate. Good. S. Start S is symbol. Now let's get rid of one of the stars and let's do a copied there. And then let's stick a borrowed there and get rid of the star there just so that everything looks a little bit nicer. So we found this symbol in what's left. Then we can go left.remove pause. Okay, I'm pretty comfortable with that. So effectively what we've said here is for every cell that we care about, we get its choice. If it's a single value, and we can find that value in the list of things that we need, we remove it. So if the quadruple said like 1122, and we found A1 and we found two twos, then what we would be left with is a vector that contained A1. So let's run again. That couldn't solve, that's fair. Can we panic with QState? Yes, we can. And we can see that we have some choices. I'm actually going to pretty print that just to make it a little bit easier for us to read. So, in the quad state, we know that these are the 4 cells in order. What's currently possible. And at this point, the given digits will have had some effect, but not necessarily a lot. And we have unfilled cells, and we have which symbols are left that we need to fill. And all we're going to do is we are going to say if well, what we want to do is do a constraint if possible. So let's do qstate.constrain borrow mute, well, just pass in state, self and state. And now we need to implement that. So quad state, constrain. We're just going to take a borrow self. It's going to take a quad, which is a borrow quadruple, and it's going to take a state, which is a mute solve state. And the reason I'm doing this in a function is because we might want to use this later as part of our actual constraint logical steps. Give me one moment, please. Okay, there we go. I was just opening a can and I didn't want to deafen you all. Eventually, this is probably going to return a logical step, but let's worry about that a bit later. Constraining is just going to be an if self.left.len is equal to self.unfilled.len. Then we know it's worth doing a constraining operation. And the constraining operation that we can do is just to say that the unfilled cells can only be the values that we have left. So let's do let choice equals self dot choices. Ooh. What we'd like is we'd like to build the choices for these symbols. So this is effectively creating a blank choice for the symbol set and then unioning in the choices that we want to enable rather than removing the choices that we want to disable. So this is, in fact, a point at which we're going to have some fun with symbol set choice. So let's mute left equals self.left.iter.copied map. Given a cell, is it a cell? No, it's a symbol. Given a symbol, we need to turn that symbol into a symbol choice. So this is going to be symbol.toChoice. And let's go and implement that. So generate that method. So we're now inside symbol ID. And what we want to do is turn this into a symbol choice. Now we know that we can't do that directly inside here because raw choice is here. So let's come over to puzzle where we also have this, and we're going to go pub fn to choice symbol choice, and let's see what we can do. So we know that the set and the symbol is self dot into parts. We now want a symbol choice that represents that. So if we say symbol choice raw symbol choice. Is that right? No, symbol choice has a set and a choice, which is a raw symbol choice. Right, so symbol choice has set, which is a symbol set ID. So it's actually self.symbol set, and choice, which is a raw symbol choice, new from empty. We're going to have to do this the hard way. Choice is raw symbol choice default. Choice dot, I'm going to say add symbol, and it's going to say, well, you can't do that. So what the heck can we do with our raw symbol choice? It's been so long. So raw symbol choice has an any, which takes a size and gives back the any for that symbol set. It has, these are questions. So as well as an any, I'm going to have a pub create none. New, in fact, I'm going to call it new single. Which is going to assert that the symbol is less than 32. And it's going to return self. One shifted left symbol. In fact, I'm going to call that new unsolved single because that is the correct term for all of this. So now choice is going to be a raw symbol choice, new unsolved single of symbol, which means I can get rid of those. And we are there. And that's not needed. And so, in fact, we can do self.symbol index there. And we're back to being good. So we now have an iterator of symbol choice. And so I'm going to reduce that, which gets given an A and a B. And we're going to return A or B. And that gives us an option, and we're going to unwrap it because we know for a fact that we have some of these symbols because we've just said an if left.len is equal to unfilled.len. In fact, here we're going to have a very quick shortcut, which is going to be if self.left.len is empty, return. There's no constraining to be done. Okay, so what we have now is we have a symbol choice, which is the set of symbols that we need remaining in the quad, turned into a singular symbol choice. It doesn't need to be mutable at this point, which is nice. And now what we're going to do is every unfilled cell we're going to restrict to this symbol choice. So we're going to have removed or otherwise constrained. So we're going to go for cell in self dot unfilled. It copied. We're going to go C choice equals state dot choices quad dot cell quad dot set. So that gets us the choice that exists, and then we're going to go state dot restrict. Oh, in fact, we can do restrict. Cell and quad.set. And it's going to give us a mismatch types. What's going on? Expected a symbol choice. Found a symbol set ID. Of course, what you want to do is restrict you to what's in left. Expected empty found effect. So now we have an effect here that we're meant to use. We'll convert it to a Boolean. And we'll just silence it with a semicolon for now. So constraint didn't need to be told the quadruple at this point, but you know, it is what it is. We might need it later, and we want to know whether overall we have made any changes, but we'll save that for later. So we're doing qstate.constrain like that, and for now I'm just going to go if that dot changed println did a restrict, which I don't expect to see because realistically we haven't done enough work to be able to perform a constraint like that yet, but that's okay. At the moment, this is all that constrain can do, and we've done what we can. So our next step is to try to write a logical step for constraint that attempts to use that qstate to do some more work. And that work might, for example, be to notice a hidden or a hidden single or that kind of thing, where only one of the cells that needs to be a foo can be a foo, and then we can go from there. Oof. Right, okay. So we need to write a logical step. And the moment we see that println turn out, in fact, I'm going to change that to a panic. The moment we see that come out, we'll know that we need to change constrain to actually tell us about the effect. But until then, I'm not going to worry. So the constraint only has prep board at the moment, and we now need a logical step. So let's teach it that. You know, make a logical step like technique. Create technique. Do we pub use techniques star? Yes. So that is valid. So make a logical step like technique. FN logical step, taking a self and a state, which is a borrow mute solve state. But we're just going to do that for the moment, and then we're going to come here and remind ourselves it returns a logical step. And so the default logical step, no action. So like a technique, this permits constraints to perform logical steps. Constraint steps happen before trying the main techniques. So it's likely on any given round it's likely to not be able to work every time. Yeah. If you do not need to do this, you do not need to implement this function. The default is to take no action. Good. Eventually, we might need something that says, hey, I'm broken, but we'll worry about that later. For now, we're assuming that we're only ever making logical steps, and therefore we can't break things. We just may not be able to continue. So we want to implement logical step. So let's pull that in. We're definitely going to be mucking about with the state. And the first thing that we need is the quad state. And we're going to perform a constraint operation. And oh look, we now need to be able to say we did a constraint. So in fact, constraint is going to have to return a logical step, and we're going to have to think about that. So we're going to prepare an action. And we're going to start with something that's like, you know, quadruple at, and then we're going to go action dot push cells, quad dot cells. What does push cells take? It takes cell info, so iter copied map state dot cell info for cell, push str colon space. So if we do nothing, that's a logical step, no action. And if we did some work, then here we're going to say that we restricted the cells, that we restricted this particular cell. This is going to be action dot push. Let action equals action dot clone. And now we're going to be told there's no clone. So logical step is going to need to implement clone, which I'm fine with. And here we're going to go. Oh no, we can do this differently. We can say let's changed equals empty vector. So if this cell changed dot push cell. And then here, we're going to go somewhere, and then here we're going to go logical step, no action. So we're going to go if change.is empty, action push str restricted cells action dot push cells changed into iter map given a cell state dot cell info of cell push str to action dot push symbols how do I get a choice into symbols? Left dot options. That gives us symbol IDs. Map given symbol state dot symbol symbol return action. Okay, so if we do a constraint, we'll get told. We don't care about it for prep board because we're going to do those things silently for now. But we may actually report something later depending on our mood. But we're going to we're going to go match qstate.constraint. And if you have no action, then we're going to do nothing. Otherwise, we're going to return that. And the reason that we do that is because if the constraint did nothing, that's fine. We can try to continue with our logical step. But if it did anything, we should return that information. So again, at the moment, this is not going to solve anything. And so what we need to do now is we need to think about how we're going to implement the rest of what quadruples could do. Before we do, just because it's frustrating me no end that we're printing the puzzle data out, I'm just going to comment it out. Neater. Good. Okay. So now what we're interested in doing is working out what we can do with the quad. And what can we do with the quad? So there are a number of things that we can do. The one that I'm going to do first is so it's a naked single is pointless because the naked single technique will pick it up. Hidden single is worthwhile though, because we have a different kind of region to what the hidden single step can do. So let's have a go at hidden single. Have a go at hidden single in quads. So hidden single, if you recall, was a case of looking at the quad state. Sorry. Hidden single is looking at the region and finding the one cell that can only be the one value that we care about. So for quads, the way that we're going to do that is we're going to look for cells that can be any of the symbols that we're looking for. And if we can't find them, sorry, if we can find only one cell that can be a given digit that we're looking for, then we can set that digit. Whew, right. So let mute found equals hash map new. For cell in qstate dot left, sorry, unfilled. For symbol in state dot choices cell self dot set dot options. Haha, there we go. Right. Found dot entry symbol dot or default, and that's going to complain now, so we're actually going to have to define this as being a hash map from symbol ID to a vector of cell index dot push cell. So that's created a map of this cell has, sorry, this symbol is found in this set of cells. Now, we only care about the symbol if it's one of the ones that we want. Yeah? And qstate left has those symbols. So we're actually going to say if qstate dot left dot contains the symbol, then we care about it. That just does the restriction that we need. So now what we want to do is say if any of those symbols only has one cell that it can be in, we're going to force that cell and return. So now we're going to go for symbol, comma, cells in found dot into just in found. If cells.len is 1, i.e. there is a single cell that can be this symbol, then it simply must be that symbol. Yeah? Now we had quadruple at, quad cells, blah, blah, blah. This chunk we're going to stick in our impl quadruple. See, can I extract into function? And then we're going to move that function up into here. And it's going to be just call it name. What we'll call it prep action. And we're going to return an action. And instead of quadruple, that's just going to be self. And then here, that's actually going to be quad.prep action state. And that's not a self, it's a borrow self. And that format doesn't need to be a format. And we don't need the .toString because it takes an impl into string. So we're all good. Right. So this means here we're acting because we know that this cell hasn't been filled and we know that it's the only place we can put this symbol. So we're going to go let mute action equals self.prep action with the state. And we're going to go action.push str set push cells sum state.cell info of cells 0 action.push str 2 push symbols sum state.symbol symbol. And we know this is going to make a change because it was unset before and now it's set. So state dot set symbol cell symbol return action. It's not cell, it's cells 0. So we're still not getting anywhere. That's okay. We're not expecting to yet, necessarily. So we had to go, it's a hidden single, and we didn't get somewhere. Let's remind ourselves of the pattern of this. See? There we go. So if we remind ourselves of the pattern here, one of the first deductions that we made, if you recall, was where the 4 went in this quad. So that should have been a hidden single because that 4-5, that 4Cs, that 4Cs, there's no way that that is not a 4. So I must have fluffed up. And I'll tell you how I fluffed up. Nothing is calling logical step. For pity's sake. So, here in logical step, we first step the techniques and then we finish. Here, we're going to step the constraints as well. That should be like that. So no action. We didn't do anything. Finished. We do nothing. And anything else, we return that. So our single logical step is now going to step the constraint. Haha! So hidden single is enough to complete quad bike. So quadruple at row 4, columns 4, 5 and 6, and row 5, columns 5 and 6, sets row 5, column 6 to 4. So that was that first hidden single. In fact, let's just update this text ever so slightly. Sets hidden single in. Yeah, so it sets hidden single in row 5, column 6 to 4. And in fact, we can be a little bit nicer there. We can say hidden single that. Well, we can say forces. We can say sets. And that's in. Yeah. So hidden single 4 in row 5, column 6. And then we get some more quadruple operations. Then we get a whole bunch of naked singles. Then we get another quadruple operation. And then a whole bunch of naked singles, and we're finished. And if I pull across the quad bike thing here, and I ask for a solution path from F puzzles, we can see it's a bunch of naked singles. Well, that's okay because they're doing naked singles before they do quadruples. Then some hidden singles, then the quadruple that sets that 4, and then some more. And they only use the quadruples twice, where we use them more because we see them earlier. That's perhaps a bit disingenuous. We're solving it, but perhaps we're using the constraint more than we need to. So let's think about that after we've made some commits. Do I have any more printlns? No. Good. So we're going to git add Kaji rules. No, let's git diff Kaji source symbols first. Right, so that's that new unsolved symbol. Kaji add new raw symbol choice new unsolved single. Kaji source puzzle includes running the constraints. So let's git add -p that. We want that bit for now. We don't want that bit. Add symbol set and to choice to symbol ID. Teach constraints to have logical steps. Initial quadruples constraint. What's left is just that. I'm going to be a little neater about this. I'm going to get rid of the commented out lines because we just don't need them. You know, we are content with knowing that the data structures that we're producing are reasonable. Right, I'm just going to push that. So in the next half an hour, which is about the maximum remainder of what I'd like to stream today, what I'm going to try to do is I'm going to try to make it so that we can interleave techniques and constraints a little bit, because it's not fair that that constraints always happen before techniques, but sometimes techniques might be harder than certain constraints actions. So, for example, I'd far rather do the restricting within a quad than I would an X-Wing. You know, as a human being, I'd far rather think about those than think about X-Wings. So what I'm thinking we will do is we will add to every... we will add to the constraint. I'm going to go one further. I'm going to get rid of unused imports and just generally tidy up any warnings that we've got. So choices is never read in quad state because we're just not using it for whatever reason, but we will eventually, so I'll leave that be for now. So actually, that's just one unused constraint, one unused import. Never mind. There's me trying to put off doing some work for a moment or two. Okay. At the moment, we run all the constraints, and then we run all the techniques. But what we'd like to do instead is we'd like to have some indication of how hard or easy a technique or a constraint is to work with. And then what we can do is we can order the techniques and the constraints around that. So they'll be in order of when they were added, but also by difficulty. If that's fair. Does that make any sense, Daniel? There's one other option, and that's that we could clone the quadruple constraint and make it a quadruple technique as well. No. No, because then I could just have prep board in technique and constraint needn't have existed. I don't want to do that. Instead, what we're going to do is we're going to say how hard or easy we think a constraint is for a human being to execute on, and then we'll order it based on that. So in puzzle, we're going to have... Is that fair? We'll do it in consts, because these are, you know, difficulties. And we'll make the difficulties a use size, and we'll set up some reasonably well-spaced difficulty numbers. And we're going to say that when you add a constraint and when you add a technique, you need to supply a difficulty. And we will order then within for when we try to actually execute on these things. And I suppose that then brings us to something a bit like the Sudoku Wiki scores, because they, you know, say, okay, there are some simple strategies like hidden singles and hidden pairs, and then there are like very difficult strategies like you know, jellyfish, for example. So what we're going to do is we're going to say how hard do we think a particular constraint is on some kind of scale. Do we want to struct difficulty that we can then bump? No, we're going to keep it simple, stupid. The difficulty rating for very simple techniques, such as naked or hidden singles. Pub const difficulty trivial, and we're going to make that 1,000. The difficulty rating, and actually I'm not going to make it a use size, I'm going to make it a use 16, and that sounds a bit weird, but then what we're going to do when you add anything into the puzzle is we're going to take the difficulty you've given it, shift it left, and add a monotonic counter so that the ordering in which you add stuff act as well. So if you add 5 things of difficulty trivial, we do deal with it in the order you gave us versus worrying about other things, you know, for slightly complex techniques such as small tuples or small pointing sets. So that is going to be 2000. And then techniques such as small fish or quadruple, such as small fish, such as quadruples, or similarly small constraints. That will be 3000. Small fish, some kinds of lines, etc. And, you know, we'll worry about the exact ordering and so on later. Or fiendish things such as larger fish. And now we're going to take advantage of the fact that we're U16, so we're going to go 16,000. No, we'll go 10,000 for fiendish. Trivial was 1,000, so we're going to go 5,000 for medium, 8,000 for hard, and 2,000 for easy. So it just spreads things out a little bit. Okay, next stage, we're going to have constraints and techniques have a difficulty. So they're going to have so how hard is this constraint to make logical deductions with? Const difficulty U16. And when we add this in, all of our constraints aren't going to build anymore. And we're going to be told that we can't make it. We can't make it din constraint because it's now got an associated constant. So in actual fact, this is going to be a function. This is going to be fn difficulty, which doesn't take anything and gives back a U16. And we're going to default to difficulty easy. Are we allowed to do that? No. We're going to say that it can take borrow self. That makes it object safe, and I suppose allows us to say, okay, well, yeah, because now the fish can look at how big they are and therefore say how difficult they are. That's good. Yep. Do I want to default to difficulty easy or default to difficulty fiendish if you don't specify one? I'm going to make it so you have to actually specify it. You may use the constants from the Kaji crate. For example, difficulty easy. Do we import the consts? Well, we do now because we did before. Yep. Except we're not going to because we're about to not use this. If I cargo dock, how many things are broken? No item named consts in scope. Yes, well, that's great. Consts difficulty easy. There we go. Right. Okay. So we're also going to have that function in technique because of course we are. And that's going to break all of our constraints and techniques. So let's teach those how to work. Given digits says difficulty 0. We don't do logical steps, so no difficulty. Quadruples. Let's get our difficulty in. And what was the difficulty that we defined for that? We said quads are around medium. Right. Singles. We have a couple of failures because we have naked single, which is trivial. And then we have hidden single, which is just ever so slightly harder. So that's going to be, yeah, just like a little step up in difficulty. Tuples. So tuples have a max n. So this is the first point at which it's valuable that this is a method. Not all trait items are implemented, correct. So naked tuples. Let's have a little look at the constants and decide. So I think naked tuples are trivial if they're two tuples. So we're going to go match self dot max n. 0 to 2 are trivial. These are naked, remember? 0 to 2 are trivial. 3 to 4 are medium. And 5 onwards are fiendish. And we're going to repeat that for hidden tuples. Except in hidden tuples, instead of trivial, it's going to be easy. Instead of medium, it's going to be medium plus 100. And fiendish plus 100. That pushes us just a little bit out based on that. Next, we have pointing. Pointing has a set, but it doesn't have a maximum size because the pointing cells are, it doesn't particularly matter. In practice, we're looking for region overlaps. So if you've got, 6 cells point at another 2, that's good enough. So we're going to have our missing members and we're going to return for pointing. I believe we said easy, but let's double check. Small tuples or small pointing sets, yeah. So in practice, we don't have any control over how big the pointing set is that we allow ourselves to act upon at the moment. So we'll just say it's always easy. Finally, we have our fish. We have big commented out chunks of code in our fish. So we should probably deal with that a bit later. So our missing member depends on size again. So remember, 2 fish is an X-wing. So up to 2 is medium, I think we said, for small fish. No, we said hard for small fish and fiendish for larger fish. So hard for small fish. 3 to 4. 3, remember, is a swordfish and 4 is a jellyfish. Fiendish, and 5 onward. Fiendish plus. So fiendish is 10,000. So we're going to stick another 5,000 on the end of fiendish. Really hard when you're dealing with, like, whatever those are called. Bogglefish. Did I even give them a name? No, I said they're unimplemented. So, you know, that should never happen. So in fact, let's say unreachable. Okay, so now we have our difficulties fed in. What we need to do now is to order the set of things that we're going to do during a logical step. So let's come down to puzzle. Let's find logical step. And let's gather and order the steps. So here we're actually going to have an enum step, which has constraint, borrow din constraint, technique, borrow din technique. We're going to impulse step. We're going to have a difficulty. Oh, I said we were going to add these things in a way that kept a counter, didn't I? So actually we need to come right back up to here. Constraints are now, well, they're going to be, they're ordered by difficulty. Techniques are ordered by difficulty. Sugar. I'm going to go logical actions, which is a vector of logical action. And enum logical action has a constraint, which is a box din constraint, and a technique, which is a box din technique. We're going to get rid of constraints and techniques. And we're going to come down here to where we're initializing, and we are going to prepare our actions by having a co-iterator of techniques and constraints. So we're going to go let mute constraints equals constraints.intoIter.peekable. We're going to go let mute techniques equals techniques.intoIter.peekable. While constraints.peek.isSum or techniques.peek.isSum. No. Loop. if constraints, what can it go? Yeah. So next con is constraints.peak. Next tech is constraints.peak. If next con is none and next tech is none, break. I'm going to go let mute logical step. Is it logical steps or logical actions? Logical actions. Equals vec. And we don't pass in constraints techniques, we pass in logical actions. And now we need to complete the work. So, if neither of them are sum, then we've finished iterating through constraints and techniques, and so we're done. Otherwise, what we need to do is we need to go, which of these two has a lower score? And we're going to prefer techniques over constraints, because techniques are like universal across all the Stokey puzzles, where constraints are per constraint. So if the next constraint's strictly easier than the next technique, we're going to push the next constraint. Otherwise, we're going to push the next technique. If next con dot is okay, if let sum next con equals next con. So there is a constraint to consider. If next tech is none, or no, if let sum next tech match would be nicer. Match next con next tech. So sum con sum tech sum con none none sum tech none means that we don't need to do that. So let's go. So let's do the simple ones first. If there was no next tech, but there is a next con, then what we actually want to do is take the next con and work with it. So this is going to be constraints.next. So we're not actually going to use that constraint. We just need to know that it's there. And we're going to go logical actions push, logical action constraint, constraints.next.unwrap. And if we do that here, then it will be techniques.next.unwrap. Here, we need to ask the question, is it the con or is it the tech that we care about? So it's going to be if con dot difficulty is strictly less than tech.difficulty, we're going to push that, else we're going to push that. Okay. I believe that now constructs what we need. puzzle logical action doesn't implement debug. That's fair. Okay, so the initial board, we were previously iterating the constraints. What we're now going to do is we're going to go for constraints in self.logical actions. If let logical action constraint equals action, there we go. So there's running the initial board. This does mean that we're going to end up no, because if we add later can flip. Just thought before I do this, I need to do constraints dot sort unstable by key v dot difficulty. You're going to complain that that can't be mute. You are. Where's the fix for that? Techniques, sort unstable by key. V dot difficulty. Good. So we're actually going to apply our constraints in difficulty order as well when we initialize, but that's fine. So, add constraint is in puzzle. Do we need it? No. Which makes sense. Logical step, on the other hand, now has to very carefully think. And realistically, what I'd like to do is logical action here is going to have a logical step function. So it's just fn logical step, which takes a borrow self, and a state, which is a borrow mute solve state, and it returns a logical step, and it goes match self, constraint C becomes C dot logical step state, technique T becomes T dot logical step state. And now here, rather than for constraint in, for technique in, we can go for action in actions. So now we're back to everything should just work. And if we go run, this time we're going to get a hidden single, then a quadruple, then a bunch of nakeds, then a quadruple, and then a bunch of naked singles. So we use the quadruples way less because we end up doing hidden singles and naked singles. So that matches better to what fpuzzles was doing. Teach. Well, it's just we're going to add difficulty levels to techniques and constraints. Okay, so we're getting on, and I think next time we're going to look at potentially some more constraints. So let's just jump back to fpuzzles for a moment. Let's make a new 6x6 grid. and let's think about what's going on here. In fact, I'm just going to refresh fpuzzles because that will make my life a bit happier. I'm just going to go 6x6 because the things are a bit bigger, but obviously we wouldn't necessarily be doing 6x6. But there's a whole bunch of constraints that we could be thinking about. And what we want to do is we want to find another constraint that we can implement next time that doesn't require values, because we're going to end up with needing to add support for values before we can do anything else. So, oh goodness me, it keeps jumping off. So extra region, we already do. Odd and even need values. Thermo needs values. Palindrome doesn't need values, so that's a possibility. Needs values, 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 values. This only needs symbols to be orderable. So if we defined that symbols should always be inserted in value order, we'd be fine, except... No, because if we had doublers, which is a thing we've been thinking about, then skyscraper would need to be values, difference needs to be values, values. Clone doesn't need values, so clone and palindrome, amusingly on the same vertical position here. Values on arrows between lines minimum, maximum, row indexer, column indexer, box indexer, XV, and we've done quadruple. So palindrome and clone will be our next targets. Unless we think that palindrome might need values as well. Just trying to think whether we think palindrome will need values. If you had a puzzle, and I'm just going to pop a palindrome line in for a moment. Let's say, you know, that wouldn't work. But that would. Yeah? I think. Yeah, fine. So... in this case, what we know is... oh no, yeah. We know that whatever's in that cell is in that cell, whatever's in that cell is in that cell, and whatever's in that cell is in that cell. So it's just like clones, normal palindromes. But what if we were to say that with doublers, you know, let's say for a moment that cell was doubled, then maybe, you know, a 2 there that was doubled is a 4, and that therefore could be a 4. Now, obviously, fpuzzles isn't going to be happy that that's a 4 because it thinks that breaks a palindrome rule. But we might want to think of palindromes like that if we don't want to think of them as requiring a symbolic clone. Clone, on the other hand, I think it's fairly clear that they must be the same. And so to me, if this was a clone pair and that was a 5 that was doubled, that would have to be a 5 that was doubled. So I think it's fair to say that clones just mean that every symbol set must have the same value on the other side. So is it fair to say, therefore, for palindromes, every symbol set must be the same on both sides? I'm going to go with yes. So that means that we could implement clone and we could implement palindrome because they only care about symbols. But we couldn't implement anything else because it cares about values. So next time, we're going to implement clone and we're going to implement palindrome because they're the last ones that we can think of at the moment that are rules that fpuzzles knows about, at least, that require only stuff that we can currently do. We'll also add in positive and negative diagonals because they're just free extra regions. But I think, unless I'm, yeah, so they just end up as rules that are marked as true in the JSON, where if instead of having like the positive diagonal, we said we're going to have an extra region, and that extra region was like there, and there. Then when we pulled up the JSON, instead of having diagonal minus, it has an extra region with those cells in. So diagonal plus and diagonal minus are going to require us to probably convert that during the fpuzzles load into extra regions. So there we go. Our goal for next time will be disjoint groups, diagonal plus, diagonal minus, and then implementing clones and palindromes. I hope that that was interesting for you all, and I will see you next time.